Okay, we will get our lecture underway here. I've got the video all started. Let's see. The last time we talked about the fact that electric companies would do well to interchange power with each other, particularly if somebody has cheaper generation than the neighbor with the expensive generation would shut down its plant, or at least curtail it quite a bit, and buy from the cheaper one. And that way the cheaper guy sells, makes money by selling, and the neighbor that bought makes money by saving. And they often would split the savings. That was a gentleman's agreement between the electric companies. The electric power industry in the United States was very friendly as far as cooperating with each other, and they did not consider each other competing businesses. They considered each other, because they were regulated, all of them, as just friendly companies in the same industry but serving different regions. And they would cooperate with each other on just about everything. That's not the case today. Today they do compete. But let's come back now and start. Let's talk about there's more problems than what we got all the way into. So I'm gonna draw an example today, and I'm gonna say, well, here's company A, and this is not meant to be a diagram, electrical diagram. Here's a communication circuit, telephone, and so A sends a quote to sell, and he quotes a price and a megawatts. So the price would be in dollars, and here's megawatts. I would just put an X. Here's $2 and X2. So this is the price is going up, and the amount of megawatts is going up. And he made, you can set it up so they can do it any number of blocks like that. And this gives this guy some idea of which block to buy, how much he wants to buy, based on the price. Remember, he's lower priced than this one. A is lower priced than B, so B would want to pick a price that's nearly his. He won't pick one that's greater than his own. Why should he buy it at a higher price than what he can generate? But on the other hand, he will buy at a lower price because he'll save. So then he gets back and says, okay, buy. He's going to buy X sub I at dollar sub I. So he comes back and says, okay, I'll buy this much. Meanwhile, company C gets a quote from B. Oh yes, they can buy and sell. So he gets a quote to sell, and he can choose to buy back to B. Meanwhile, D over here sends him a quote, and he can buy from him. And of course, you probably figured that I would close the circle and say, look, he's gonna send him a quote, and he can send a buy. Now, these are each called bilateral because we're at any one time we're only dealing with two. So it's A and B, and then it's B, it's so forth. So we're only dealing with two of them, bilateral transactions. Now, there's several things that come up well, how do I know? I mean, he's going to buy from A, then he's going to turn around and sell. Well, should that come before or after he does the buy? Because once he does the buy, his prices change. Similarly, he's going to make a quote, and then he's going to buy. The order of these things, we showed that yesterday. We showed that in the example that I'm not last Tuesday, not yesterday. The order affects what the prices are, and this can be. You can see here, just with 4 of them, how complex it gets. And so the companies realized that they needed to do things differently. They needed to do things differently. And thus was born what we call a spot market. And in a spot market, a spot market is not one of the utilities. Let's say it's a separate entity that does this. You could have it that it does it for a fee. It takes a little cut from each transaction, or it's simply supported by subscriptions, meaning fees to the member companies to use. So here's the spot market, which they call the broker. And here we had loads. Now, it could be a load. It could be a single load, like a big steel mill, but more likely it would be a municipal. All over the U.S. in the rural areas, municipal utilities. The town is served by a municipal utility, and the municipal utility buys power from somewhere. It's delivered on the high voltage transmission system. It gets into the town, and it gets dropped to distribution voltages and then to the customers. The municipal utility simply bills at whatever its rates are, and it gets out there and it buys the power on the open market. And that kind of system works very well. So that's a load. I mean, you can just put it in here as representing a load and so it sends a message in here, and it sends in. You can call it a bid to buy. Okay, and so we'll see this later. This is I'll buy so much megawatts at this price. If the price is lower, I'll buy even more, and so forth. Now, that variability assumes that the municipality probably has some generation of its own, and when it decides to not buy, and if it has more load to fill, and it hasn't been able to buy it on the outside, it generates it by itself. I have to tell you this little story. The first town that I lived in when I started working, when I got out of my master's degree program, was called Lansdale, Pennsylvania. Lansdale, Lansdale, Pennsylvania. It's north of Philadelphia, and we were in an apartment there, my wife and I, and the town had a municipal utility, and it had its own small coal-fired power plant. And this was one of the problems with these municipals, that they were small, and if they're far away from everybody, well, that's all you can do is build a plant. Maybe you don't have any connections to the outside, or maybe you do, but they don't have any power to sell, so you have to generate your own. And the problem with theirs is that it was coal-fired. It was quite dirty. The people in the town hated it. Hated the soot that came falling down from the coal-fired power plant. And just about the time we moved in, they shut the power plant down, built a substation with a big transformer, and connected to the Philadelphia Electric network, which was what the big electric utility was, covering obviously the city of Philadelphia and much of the surrounding suburbs. And so suddenly, I think they still build directly from the municipal, but the municipal bought power as wholesale power from Philadelphia Electric. Now, they weren't doing it as a broker, and they bought from Philadelphia Electric. They had a contract with them. They probably paid a regulated amount. Anyway, we also have generators over here. Here's a generator, and let's just put a box around. He sends bids to sell. Bids to buy and bids to sell. Now, how do you decide who is going to buy and who is going to sell what? And we're going to talk about that quite a bit in our examples today. So the first thing I'm going to do is run an example from a, let's see, where we go, here we go. This is from a test problem that I gave in 2008. So you're going to start to see some ancient history here. I hope I can get the rest of my paper to work a little better than that piece. Anyway, here. So here's my system now. I'm going to say that I happen to have a 2-bus system. Here's L1 and here's G1. This ought to look familiar. It doesn't have the same numbers in it. G2 and L2. And this has a max flow of 60 megawatts. Now, we're gonna decide who generates what and what loads buy what by bidding. Assume that these are far enough apart; they are not part of the same entity. You don't have a control system that's connected to each one. They're just out there, and we'll assume that we have a broker up here, and that there's communications to the generator, communications to the loads. The broker decides who's going to buy what and tells them what the answer is. This could be used back for our page 1 where we had A, B, C, D. This scheme would work for that too. So I'm going to show you, but now we're going to do if you remember, the way we solved it before, we just ordered the blocks of bids to sell in an ascending cost, and then we just started picking them from the lowest to the highest. So if there's generation only, then you order blocks lowest to highest, and then pick one block at the lowest, and then calculate how much is left, pick next the next lowest, call it that, which is the next one as you go higher. You keep stepping until all load satisfied. Very simple scheme. We did that when we had the the loads and generation on. We showed that before, but in that case, the loads just said, look, whatever the price is, that's what we're going to pay. So in essence, the load was a fixed amount, even if they were in blocks. Doesn't matter. They just think what one had 500, the other one had 400, whatever it was. Now this case, the loads are going to say, well, you know, I'm not going to buy everything you offer. If your price is too high, then the load is not going to buy that much. Okay, so here are the blocks, and you'll get the problem sheet that I will extend to you, which looks like this. But I'm going to write the numbers down now. I'm going to say here we have, and I decided here. I should have called it a block. I called it a block number. But I gave them alphanumeric names, and so I said for generator 1, it had 2 blocks, G11 and G12. Now you know it's from generator 1, and it has 2 blocks, each 150 megawatts. So that's the megawatts, and the price, which is dollars per megawatt hour, would be 10 and 30. So he'll say a lot if you want to pay 3 times, but he'll say the first 150 for $10, the second 150 for $30, and then you go over to generator 2, and he only has one block, and that is called G2-1. And that is 150 megawatts, and the price is 20. So this is again dollars per megawatt hour. So that's 20. So there's 3 blocks of generation. Now we come to the loads, and here's load 1. So he has a block L1. Pardon me, L1. -1, and that's 100 megawatts. He's willing to pay $80 per megawatt hour. Load 2, I'm sorry, it's not load 2, it's still load 1, but it's load 1 L2, L1-2 is another 100, and he's willing to pay 60, lower price. He's essentially saying, if you lower the price enough, I'll pay more. Now, it says that the loads have a certain amount of power they want to buy, and if you keep raising the consumption, that price of willing to pay goes down, now if it's flat, well, then there's just one block. So then there's load 2 over here, and he's got L2-1 and L2-2, and these are each 100 as well, and the price is 70 here and 50 here, dollars per megawatt hour. This is megawatts. Okay, here's megawatts. So we've got, I can draw a little dividing lines here. So here's generator 1, generator 2, and load 1 and load 2. Now, the way that we solve the problem, the way you solve this problem is to draw again, and you're going to look at this, and when you see the numbers, you're going to say, yeah, but you picked the numbers so that they would all look nice and round off, and they would match up, et cetera, et cetera. You're absolutely right. This was a test problem. One of the things that's a big challenge to a professor, believe me, it's a challenge, is to come up with tests which are doable in an hour or two. It's easy to come up with a problem, but if you make it so complicated, nobody has a chance of finishing. That doesn't prove anything to anybody. It just proves that you can swamp them. Any professor can do that. But what you want to do is give your students a problem that you have a chance to finish, to show that you really know what you're doing. All right, here we go. So what I'm going to do is I'm going to put all the generator blocks, and I'm going to put them in ascending price, okay? Price is going to go up. And I'm going to name the blocks. G1-1 is 100 megawatts at a price of 10. Did I have that right? Yes. At a price of 10. Now, I'm actually going to split this up because I want to be able to break it up. I don't like that 150. So I'm going to say I have another one from G1-1, which is actually 50, which is also 10. So that's the same block. G1-2, which is 50 at 20. G2-1, which is 100 at 20. So there's the other 151. This is G2, I'm sorry, G2, let me get it right, G11, G21, I mixed those numbers up, G21, and finally G1-2 is 100 at 30, and G1-2 is 50 at 30. Okay? Blocks of 50 are evenly divisible by 50. And here's the loads. Now here, I'm going to list the loads in decreasing price. So here, I'm going to say L1-1 is 100 megawatts. This is the megawatts, and the price is 80. L2-1 is 100 at 70. L1-2 is 100 at 60. And L2-2 is 100 at 50. Okay. Now, what I want to do now is I want to start to match them up. And here is the rule, and we'll come back to this. We'll come back to this later. But there's a matching rule. There's a rule to match things up here. And the rule says match the lowest priced generator block to the highest priced load block. So the lowest priced generator block to the highest priced load block, which says that we sell off the lowest priced generator blocks first, and we supply the highest priced load blocks first. And you keep matching until you're left with a situation, well, either you're out of generation or there's no more load to supply. Let's forget that one, but until you have a generator block, okay, which is higher priced than remaining load block or blocks. Once that happens, you stop, you quit. Okay, and you may not sell all the generation, or you may not sell all the load. Now let's see. In this example here, we've got I'll put this in here. We've got 450 megawatts to sell. Okay, we've got 450 megawatts to sell. And the load, we've got 350 megawatts to buy. Well, assuming that the prices hold up, we'll probably end up, we know that we won't be able to sell all the generation. There's just not enough load out there. But which blocks don't get sold? And maybe this thing could end up with some load blocks not supplied either. Actually, what I said before is not correct. It says I can't sell all the generation. I could supply all the load, but I may not necessarily supply all the load. So now let's see, and this is the rule: match the lowest priced gen block to the highest priced load block. I will come back later with I get a kick out of people say, okay, we're gonna give you economics 101, and as if apparently in days of yesteryear, course numbering at universities all started with course 101 as the first course. You electrical engineers had circuit analysis 101. And so forth. And I always tell people, gee, at the University of Minnesota, the course numbering starts at least at 1,000. All course numbers are 4 digits. So to update that, we'll say economics 1001. All right, but anyway, so now what we're going to do is we're going to say, okay, here's we'll put this up here. Here's the buy / sell, okay, and I should say sell buy, because it's sell on the one side. So G1-1 sell 100 megawatts to L1-1, and remember this guy's price is 10 and this guy's price is 80, so it was lowest to highest. So that takes care, and that's. And so here we can look at the flow on the transmission line. The flow is 0 because this all takes place between G1 and L1. Then G1-1 sells the remaining 50 megawatts to L2-1. And that partly supplies L2-1. So there's now 50 going over, and then G2-1 cell 50 megawatts to L2-1. Remember, this L2-1 is 100, and so there's no more. This is still 50. So now L1 is satisfied and L2-1 is satisfied. All right. So and this one went at a price of G1-1 went at a price of 10. This guy was at a price of 70. G2-1 was at a price of 20, and this one is still at 70. So initially our price spread was 70, then it dropped between 10 and 70 or 60, and then it dropped to 50. But we still have a big price spread, so it's going to make it worth their while. We haven't sold all of G2-1, so he's going to sell the remaining 100 megawatts that he has to L1-2. And L1-2 was at a price of 60 and G2-1 was at a price of 20. So there's still now we've got a price differential of 40. And what's interesting here, let's see, let me see the flow. We'll consider the flow. Flow is 1 to 2. Okay. Well, in this case, G1-1 sells 50 to L2-1, right? And then G2 sells to L2. That doesn't do anything. So that's plus 50. And then I'm looking at my answer sheet here, and I'm saying I'm sorry. Then G2-1 sells to L2-1, but G1-1, that's G1 goes to L2. That's 50 megawatts, so that's plus 50, and it ends up at plus 50. Then G2-1 sells 100 megawatts to L1. G2 sells back to L1, and it's 100 megawatts. So now this goes to minus 50. And let's see. Then G1-2 sell what? 100 megawatts to L2-2. And the price here, G1-2, is a price of 30. L2-2 is a price of 50. My differential in price is down to 20 now. So if this one, I'm sorry, when this one should be minus. No, I'm wrong. This should be minus 50. And then this one, G1-2, sells 100 over to 2, and he sells 100. So now it flips it back around again to plus 50. And then last of all, we have G1-2 has 50 megawatts left. 50 megawatts not sold, because we've actually satisfied all the load here. And the G1-2 was at 30. The last one that we sold at 60. I'm sorry, at 50. That was it, price. But there's no more load to sell. So that's not right. I said there's 450 to sell, right? 1, 2, 3, 4, 50. And there's 400. Oh, I'm sorry. This is wrong. There's 400 megawatts to buy, and 450. So there's 50 that's not sold. That's correct. Okay. But again, the principle was match the lowest price generator block to the highest price load block. Keep going until, in our case, we sold everything that we could sell. The load was all satisfied, and we can't sell anymore. So it ends with this last 50 at the lowest price generator, a G1-2. is not going to sell anything. Okay, so his price doesn't get him much. Now, what I want to do is I want to show you what this looks like so page 4. If we plot the following, and this is the economics supply, demand curves. Well, here they're not curves, they're blocks, okay? And if I put 50 and I put 100 up here. Well, now this over here, this is 500. This is megawatts here. And this is price. Price on the left, on the vertical axis. Well, the loads start out, and we had L11 that started out at 80. So we had, let's see, did I draw? Yeah. So he did this much. He did 100. So here's L1-1, and then the price dropped to 70, and we did another one here of L2-1, and then we do another dress. So this was 100, and this was 100. So we're out to 100 here. We're out to 200 here. And then the price drops down to 60, and we've got another 100, and that's L 2-1, 1-2, and then it's gonna, I'm gonna draw this out a little bit more. I'm gonna say that's 400, here's 100, 200, this is 300, and 400. So this is 300 here. This is the advantage if you're using a marker board or a chalkboard. You can erase things, okay? And so that's it. And this ends up at 400 over here. So this is the so-called demand function or curve. Now then the supply comes in, and it's got G11 at an initial price of 10. So he comes out here, and he goes all the way across at that price to 150. So he comes across like this. Here's G1-1. And then the price goes up to 20, where we have another 150. So we go all the way up to 300 here. And this is G21. This is G11, this is G11 and G2-1 at a price of 20. This is 10, and then the price is going to go up again, and it's going to go up to G1-2, and it's going to cross over like that. G1-2, And part of the last chunk out here of load is not sold. This is where things actually operate. You know, so anything more up here, the price is higher than the load. Well, the load is all satisfied at that point. And this is called the clearing point, and we'll come back and talk about that. But this is and we call this one the demand function. This is the supply. This is the supply or curve for generators, right? This is for load. So loads start out and they say, I gotta have so much power and I'll pay this much. If you make more available cheaper, I'll buy more. And so as you bring the price down, the demand curve will come out like this. Generation, it just follows that rising function. If you want a block here, then you want more, the price is higher. More, the price is higher, and that's just the cost of doing business. Okay, so that is the way that we fulfill these things in an auction or with a broker. Okay, I don't want to call it an auction. It's a broker that's getting these values in, and it's going to match things up. It's going to match things up. Well, now we'll come back to economics 101, if you will, and so let's come back and we'll talk about the economics of the spot market. Again, it looks like a broker, but there's bids to buy, bids to sell. Okay. Society is best served, okay, says the economist, society is best served when. Now here's something that we have to think about here in this problem. When the worth of load served is maximized, and the cost of generation is minimized. Now, conventional economic dispatch said whatever the load is, it's going to pay a regulated price, so it just pays whatever we tell it has to pay. That's the regulators, and they set that value for as low as they can and still give a profit to the power company. And then the power company just says, well, all I have to do is minimize my cost of generation. So conventional economic dispatch, load is fixed, right? Load fixed, and generation minimum cost to meet the constraints that's basically the way the electric companies did it for a long time. until along came the economists. And I seriously, the economists brought us many advantages to looking at the ways of looking at it, their ways of looking at it. As I said, when a lot of this got started, there were electrical engineers that worked for the utilities that aided the economists. And I didn't know what to think. I didn't like the ideas at first, but once we got into it, and you began to realize that the economists were bringing us a clearer way of looking at the whole thing. I had to admit, I know others that said, you know, this really is a better way of doing this. Okay, so we should add, we're going to max worth of load and min cost of generation, while we always have that constraints meeting transmission constraints. And by the way, you're also going to meet P-gen total is equal to P-load total. We're gonna have balance power generation, including losses. But I'm not going to get into the losses of it right now. And we can also talk about contingency limits. So you're going to meet the transmission limits themselves. You're also going to meet the conditions that any outages will not cause overloads. That's the N-1 security conditions are going to be met. So let's define. Now here's where things got very different than what we used to do. Define Fi of Pi generator cost. Yes, sir. We know how to do that. We know how to do that. We've been doing that for years. Okay, and now I'm going to define Wj of Pj as the load worth. In other words, it says it's worth so much to the load to buy so much power. Okay, and we know that this Fi, if this is Pi, that Fi is a curve like this, Fi of Pi. What is this one? Here's Pj, and it's a curve at it can either come like this or it can go like this, but it's a dropping off function. Okay, and I usually end up with this concave function, so I like to see it going down like that. But it's a curve that goes down as power goes up. Okay, well, then I can start to formulate this thing mathematically as the economist would. That says, okay, Economy 101, Economics 101. Let's do it here. At the University of Minnesota, it's 1001. And I bet our courses have got an initial leading digit of 1, 2, 3, or 4, etc. And they'll have 5 for graduates. So you all know that. But let's do 1001. And it says we're going to max the sum of the Wj, Pj for the loads, and we're going to subtract the cost from it. So this says we're going to max the worth of what we get out of it minus the costs, okay? And we hope that the worth that we get is more than the costs. If it's costing us more than the load is worth, it simply would not pay to operate the power system. So there's got to be, the power has to be worth more to the loads than it actually costs the generators. There's a difference. In effect, the economists call that the welfare. The overall societal benefit, or the overall societal welfare. I put this, I'm sorry, I should have had this bracket out here. And so it's the sum of all the W's minus the sum of the F. Okay? Well, if I'm going to max, I don't maximize things. Linear programs, quadratic programs are always, so I'm going to reinterpret this, and I'm just going to say, well, okay, I'm going to minimize, and you just do this. Fi of Pi minus the sum Wj of Pj. Same thing. If I maximize this, I can do this by minimizing this. So all I need to do is add these cost functions into a standard old optimal power flow, and I get this whole broker, or this whole dispatch that I want. So I'm going to say here, we'll use OPF, and we're going to use that minimizing function. And so let's do it again. Min the sum Fi of Pi minus the sum, gotta have a big, of Wj Pj, subject to our constraints. Well, Pgen minus Pload equals 0. Now, at this point, we don't know what the load is or the generation are. We're just simply going to say I'm going to minimize this function, and the generation, whatever the generation is, it has to equal the load. But we don't know what the generation and load values are at the front end. So. And then I could say, I could add, if you will, I can add line limits, line flows, less than or equal to limit. I could even put contingency flows and things like that. So then the next thing I will do is form our friendly old Lagrangian. Monsieur Lagrange. So, here's our Lagrangian. Equals Fi of Pi minus the sum of Wj of Pj. That's the load. This is the generation. Remember, this is gen, this is load. Plus lambda times, let me do it this way, sum of Pi minus the sum of Pj equals 0, right? So I can just put that in the constraint that way. And I could add the mu for all the different line constraints. I don't want to do it yet. Just going to solve this simple problem. dl dpi for generation equals dfi dpi plus lambda equals 0. And d Lagrangian dpj equals dwj of pj dpj minus lambda. We got a minus sign up here, equals 0. Now, again, this is we're not going to look at, we don't have to include the line constraints or anything. I'm just doing an economic dispatch, but I can do it with this Lagrangian. Well, the solution for this is that df dpi is going to equal to dw dpj at the optimum. At the optimum. So what is that telling us? It's telling us that if we take the derivative of the cost, and remember this is something that we've got to be careful. F of I of PI is equal to dollars per hour at PI. DFI, DPI is equal to dollars per megawatt hour at PI. Okay. Well, that's what we call a price. This is actually cost. This is a total cost. This is a total cost. This is price. I can push this up about halfway here. And WJ of PJ equals dollars per hour. That's how much you're going to pay at PJ, or DWJ, DPJ equals dollars per megawatt hour at PJ. That's price, okay? Price and price. So it simply says that we need to get them both to the same economic, that at the economic, or at the optimum, DF DPI equals DW DPJ. Now, we used to call these incremental costs. The economists call it marginal costs. It is a little more precise term, marginal cost. And the Economics 1001 says the most economic operation is when the cost of production is equal to the price. I shouldn't say the cost, I should say the price. Price is equal to the price of consumption. So that it says at the end that I will achieve the best for my economy when the marginal cost of production is equal to the marginal cost of consumption, or of whatever the load wants. Any stable point either side of that is not at the most optimum point. So you want to stop at those values. Well, that's this, and this is DF DP, and this is DW DP. This is the incrementals, and here's the equality point, or the crossover point. All right, now another thing that then comes into this whole thing. Before they went to a completely centralized system, a transmission operator type of system, they tried to do it they still tried to do it by bilateral transactions. One of the issues, you remember we had A and B and C and D, and these represented different deals going on. Well, the other question is, will the transactions overload the transmission system? And that's a real difficult problem. How do I know if A sells something to B, and then later on B buys something from C, or sells something from C, that eventually some line is going to overload someplace? And this was settled down by the following. They said, well, look, each area will have a web page, believe it or not. Called an open access same time information system. That brilliant bit of acronym. Is there a verb for creating acronyms? Acronymology, maybe. If you create acronyms all day, are you an acronymologist? Whatever. If you work for the government in the United States, and this is probably true all over the world, if you work for the government in the United States, you create acronyms, right and left. If you work for the military, you create them at 2 to 3 times the rate that the government does. Some corporations create acronyms for everything. Every meeting has every meeting type, every report has an acronym, and people just talk about the A2 report and the BOS meeting, and I don't know what they meant. I worked for a company once, and they had so many acronyms I could never understand them. I couldn't follow them. Anyway, the government thought up this OASIS. And it stuck. I mean, they were the government. They can make it up. And so the idea of the OASIS was that people said, well, look, I'm gonna post the transmission capacity available for different. Now I will call it paths. That's a loaded term. Paths could be one single transmission line, or it could be it could be a path like that, or it could be a group. It could say, well, it's this transmission line and this one here, and the path is this, and they called that a flow gate. Actually, a name made up by there's a footnote in one of the chapters in the book. The fellow that made that up now works for NERC, but at the time he was working on these things, they came up with the term flow gate. He took the very same course that you're taking from me when I was teaching it at RPI. Anyway, so you can look that up. But the flow gate simply says, well, what's the sum? What's the maximum flow, which is the sum of these three? Okay, so we've got PA, B, and C. So flow gate equals PA plus PB plus PC. It's that simple. Well, if you use the linear system, I'm sorry. Here we go again. This is the flow gate here, and it's got 3 flows on it, and so the flow gate is the sum of those 3. And so they publish how much power can go over, let's just call this P1. How much power can go over a single line that crosses their system, or a certain flow gate on the system. And they do studies internally to determine how much power, and we talk about that in the book and in the lectures, that they have to allow for to have enough extra capacity in case they need to move power from one generator to another in an emergency, etc. But and then people would look at it, and they'd have to know, well, how much is my transaction going to use that flow gate? And then they'd go to the Oasis site and say, okay, I want to reserve. I want to reserve this, and they would input to the Oasis. They would input a TSR, a transmission service request. Now, there's there's a company in the city of Minneapolis called OATI, Open Access Transmission International. If you're driving and you come across 494 and Route 100, you cannot miss their new building. It is gorgeous. And it says OATI Microgrid. Well, at first, they weren't in the microgrid business. They were in the business of creating the factors that people use to determine how much of each flow gate they were going to use for a certain transaction. And they built the transaction calculator and operated it. They probably still operate it. They have a big center up on the Mississippi River here on the western side of the city, where they have computer systems that are backed up, and they have battery backup, UPS, what they call uninterruptible power supply systems, and diesel gensets sitting outside that kick in. Diesel gensets from our own Cummins T&D company here in Minneapolis. OATI that did the calculator for these OASIS calculations. Okay, a little bit of local history, local flavor. But what I want to do now is I want to jump to the future. In the course, and that is that we're going to have this transmission operator, or ISO, transmission operator. In Europe, again, they call that's what they call this function. In the United States, they call it an independent system operator. So we have the mid-continent ISO, MISO, which we live in its territory. We have PJM as an ISO. New York has an ISO, etc. California has an ISO, independent system operator, and people put in bids to sell, that'll be generators in here, loads, bids to buy. Now remember, some of these loads to buy could be municipals, or could be, Xcel Energy putting in a bid to buy off of this marketplace. And this is the other term for this is market operator. Market operator. Okay, so we've come sort of full circle now. We have many utilities, but now we'll talk about this the next couple weeks. The generators are starting to act independently, and the loads act independently, and that's because they are allowed to. And the calculation is done by an optimal power flow. And I'm going to put these examples, and these are in if you watch the CUSP lectures. Example of generation and load bid dispatch on our favorite 6-bus system. And here were the 3 generator functions. So there's 3 generator buses, and here's the 3 load buses. Now you notice that the load bus, I used a linear function, so it has a high number here, much higher than these, and a negative coefficient here. So the generator functions go like this. The load functions go like that. I didn't put And this simply means that it looks like that. But if this is ABC, well, then this is ABC, and it says, well, look, you've got a B constant and a C constant. It's a quadratic function, actually. It's not very curved, and it actually starts at 0 and comes down. Ah, yeah, that's right. Load has to be negative. So here's this WJ, here's FI. Okay, so these represent the F. The top represents the FI functions, and these represent the WJ functions. And this is they're both quadratic, except that this one is just starts out and it goes boom like that. It's got a flat part up here, and then it curves just slightly. I didn't put too much curvature into there, but it's negative. Okay, and so what happens in this 6-bus system is we put the min and max in. We said that the loads would like to buy 100, and the generators can supply what, up to 350, 455, 530 megawatts. They've got plenty of power to sell, and we are going to show you the result. Here's the result. With no line limits, all the load gets supplied, so all load supplied, and there's the generation dispatch, and it matches them all up. Guess what? The bus lambdas, they're all the same, and remember, the bus lambdas are the LMP values. And here they are, 1244 for buses 1 through 6. So the optimal power flow, when it executes, minimizing F of I of PI minus WJ of PJ, effectively carries out that matching of lowest price generation to highest price load. It effectively carries that out. Now, if we impose load limits, okay, you notice down here that we're not supplying. So some load not supplied. And we have a couple of line flows that are at limit. Bus lambdas are different all over the system. They're higher at the loads than at the generator buses. And that's the solution. Now, what happens if you're a load you put in to buy so much and you don't get it from this marketplace? You still have the option of starting up one of your own generators or getting into a bilateral transactions. We can actually do the bilateral transactions right on top of these this spot market, and they talk about what percentage of sales are done. So that's one point that I'm gonna. And you'll get these two. We'll get these 2 pages in your notes, but it's important that we have a spot market. We have bilateral transactions that go on. These overlap each other. The bilateral transactions, we're going to learn later on that they have to. What should they pay for use of the transmission system, and that depends. So this sets buy, sell. It also sets the LMPs, and the LMPs, it turns out, can be used to charge for transmission. I'm getting way ahead of myself here, but that's what's interesting. Bilateral transactions. There's also long-term deals going on where people, they're done on a bilateral or they're done on a multilateral, where one generator will be selling to large groups of people that have grouped together and offer to sell so many megawatts during certain hours of the day. And it's the remainder, it's the spot market that kind of fills in the rest. But the spot market determines the LMPs, which has an effect on the transmission charges, and that affects these guys. That affects these other transactions going on. Very interesting. So we will see you next Tuesday. Where we start to talk about the market-based systems, the deregulated power systems. As I say, in a lot of countries, they've been slow to develop it. We weren't the first. The Norwegians beat us to the deregulated market in Norway. They had done that several years ahead of the United States. Then the U.S. got into it. The Europeans basically have put their foot into the water, but they're not swimming. I like that analogy. Anyway, they're not really getting it. They're not really into it yet in Europe. Other countries of the world are getting into it slowly because eventually they all realize that deregulating and operating a market is a better way to operate the power system. As I said, this took electrical engineers like me and like others, especially some others that I knew. This took us a long time to admit that this really was a better way to do it. Okay, so that's what we'll be talking about next week. And so I bid you adieu for the weekend. Whoops, wait a minute, I want to do this. Okay, and I'm going to press the button that says end the meeting. Boom, goodbye.